Hi everyone, welcome back to Line. Today we're going to work with TRELLIS.2. This is an open source image to 3D generation model used to go from image to the image to 3D model, like with extension of GLB, OBJ, which is a mesh or point clouds, and also get a video of the 3D objects. So getting a 3D object from only a single image, PNG image. So in order to do that, we need first to deploy this model. So let's understand the requirement, the prerequisite. So you can see that it was tested on Linux using the NVIDIA GPU with 24 GB of memory, using A100 or H100 GPUs of NVIDIA. The CUDA toolkit is about 12.4, and they use also Anaconda and Python version higher than 3.8. So now we have all the information, the necessary information to try building our VM virtual machine on GCP. So let's do it together. Let's create a VM. Here on GCP you can do that. So we can choose, for example, TRELLIS.2 example, then any for the zone, then here the GPU. I can choose here the example GPUs, about 40 GB. One GPU is enough for the inference of one example. Then we can go ahead with the OS and storage. It's important to go also in the OS and storage in order to change this parametering. Here, for example, the Debian by default is not adapted for our needs. We need to choose the deep learning on Linux, and then to choose the virtual machine with the 12.1 for the CUDA version, and with Python 3.8, so .10, sorry. So it's okay, it's higher than 3.8, and we can take this one. We can also change the 50 to the 100 GB, about the size, and then select. Data protection is about if you want, for example, to deploy with an API. So then we can create. I have already created mine, so I'm not going to create it again. Then we can be connected to your platform. In fact, to your VM. So let's. Okay, now when we have the IP of our VM, we can be connected using VS Code. To do that, we just need to go to our VS Code and then to connect with the remote SSH. And then when clicking on that, we can get the VM we have chosen. You just need also to get the key, the public key, and you can also debug that with a Gemini or Cloud Code, for example. So then when it's done, let's now understand together what is the content of this model. So what I suggest to do with you today is to make a comparison with a simple other model such as VAE, which is Variational Autoencoder, and Diffusion Model. So this is also suggested by ChatGPT. This version starts from a classical VAE. So what is exactly a variational autoencoder? So to understand that, a variational autoencoder, this picture is extracted from Wikipedia, variational autoencoder. So we have an input. So let's imagine we have a 2D input of an image. Then we have an encoder based on convolutions in general, and then this encoder will provide a latent space. So this latent space will respond to a normal distribution, okay, with mean and sigma as a parameter of the normal distribution. What does it mean? Meaning from an image, a 2D image, which is based, for example, on 2 dimensions, okay, and we have RGB, so 3 channels, but we have X and Y dimensions. From this image, we go to an embeddings about 512, for example, elements of the vector. Now, each element in the 512 elements correspond to a normal distribution. Meaning, if I take all the dataset and all the first element of my vector, I would see like a Gaussian. exactly in like we can see in this picture. So it's not the latent space, it's not the vector of one sample which will look like as a Gaussian. It's each element of all the dataset will correspond to a Gaussian. And then the decoder is about deconvolution to build back the image that we have at the beginning. And the loss to get that is a loss of a reconstruction, so a pairwise pixel by pixel, and also a callback, KL loss for the normal distribution. So this is about the VAE, and it's built to be able to make a generation of 2D image, and it can also be used for 3D image. We just need to image in instead of converting to a 2D image. We can get only from the latent space to get a 3D grid like voxels, and to fit and to fill in fact the voxel grids. Now here we have an example in this, so we have this link, it's an open source. We have several comparison. Let's see the author just to see them. So these are the author of this, so about OpenAI and Stanford University. So good. So let's see back. Okay, so this is our auto variational encoder. So we have our input encoder, z given x. We have the vector, the embedding, and the decoder, and then the x prime. Okay, now this about diffusion model. So the diffusion model is about, we have an image, we add noise. Okay, we continue adding noise, and iteratively in each step we're trying to remove the noise from this last step to this one, and from this one to this one, and so on. So in fact our system of TRELLIS.2 is based on the variational encoder and also on the diffusion model. So in fact for the variational encoder, so let's do it step by step. We use an image encoder, we have the parameters, sampling, and then the decoder. The loss, as we said, is the reconstruction loss plus scale divergence. Okay, but the problem of the 3D generation is that the latent space is not enough. We need to replace it by a spatial grid to have more information on the latent grid. Then the TRELLIS representation is in fact a structured 3D lattice of latent tokens. So this is conceptually a 3D grid of latent features, Z of I, J, K. Each node stores geometry information, appearance features, and object structure. The encoder in the TRELLIS.2 is about, in the VAE, it should be an encoder just of the parameter mu and sigma, and now it's depending on the X, Y, Z of our grid structure. Then we have the sampling process, and then the decoding is about, like, a common output should be sign distance field or radiance field, and the diffusion, instead of simple VAE sampling, it's a modern models like a TRELLIS.2 often replace direct VAE sampling with diffusion, and the diffusion is about what we explained. It's also using a transformer, and this is the last step. 3D transform operate over the TRELLIS grid. It allows each cell to attend to other. So now it's great to understood that the final nutrition is about TRELLIS.2, is about 3D spatial VAE, plus diffusion generation, plus transformer over the 3D grid. So I hope this explanation was enough clear for you. Let's now see how it's working now that we are more understanding that. So now the two things we just need to do after cloning the Git is to, so let me show you the changes I have done. Okay, I've done these two changes. So in the here, yeah, device map none, and the low CPU mem usage as false. You need to add that to make it working, and also in the example you need to put that at false. It's creating some bugs on the extension of the WebP, but beside that it's okay. Then in the git ignore just need to add all the things you need, and just now I have also added the revision from Hugging Space bugs for the model, because in fact the TRELLIS.2 is also depend on several other models, so you need to get access to all the models that are required. So now we just need to use example.py, okay, after running like all the instruction of the GitHub. For example, the instruction of the GitHub is about building the Anaconda environment and so on. So when it's done, you just need to replace here by your image, and then by the extension of the video produced and the GLB, and then you can output, you can extract that in fact in your local. So let me show you, okay, from this example. Now this example, we have now a 3D object, and this is very precise. It's amazing. It's really amazing. This is an example provided by Microsoft, and the example I wanted to try is this one. Let me show you. So here you see that Earth in 3D, we have this picture, and we can see this picture in bigger. Now from this picture I got that, a 3D object with all the details of a Earth. So it's very great, and I got this 3D object using TRELLIS.2. So I hope it was clear for you. I just remind you that you need to be careful about all the instruction here in the repo. So to clone the repo and then to install the dependencies, to create the new Conda environment TRELLIS.2, and to use the preprint rate, you need also to ask access to all the dependence models of that TRELLIS.2 is using, and then it should work. So that's it for this video. I hope it was clear for you. Thank you for listening to me. Please share this video on LinkedIn, YouTube, and other platforms if you want. And let's see you soon next week for next video.